Hello. In previous videos, we saw what is current density, what is current, what is the relation between current density and volume charge density. Also, we saw what is continuity equation in point form and differential form and integral form. So, in this video, we will solve two problems. Then we will move on to the different properties of conductors and dielectric materials. So, to solve problems, I will take first problem as given the vector current density as J is equal to 10R square ZAR cap minus 4R cos square phi A phi cap milliampere per meter square in cylindrical system. Find the current flowing outward through the circular band R is equal to 3, phi is from 0 to 2 pi and Z is from 2 to 2.8. So given that they given what is current density, so also they mentioned that the system is in cylindrical system. So we have to consider cylindrical coordinates. What you have to find, what is the current? So what is the relation between current and current density? So we know that I is equal to surface integral of J dot ds. But here, if you see the equation, there is a two component. One is AR component and A phi component. If you see the equation for J, there is a two component. One is AR component and A phi component. We can't say this J is normal to particular surface. If it is that only AR component, AR vector, then we can say J is normal to phi and theta surface. But here we can't say it is parallel to phi and theta surface or R and phi surface or Z and phi surface. Here there is a two vectors, two components of J. One is with respect to AR, R and other is with respect to phi. So we can't use directly surface integral here. For that we will use I is equal to surface integral of J dot ds. So this surface integral can be converted into volume integral. So using divergence theorem, I can write this surface integral as volume integral of del dot J into dV. So I is equal to volume integral of del dot J into dV. Now what is del dot J? Del dot J is a divergence of the current density, that is del dot J, which is equal to, in cylindrical coordinate system, it is given as 1 by R into dou by dou R into RJR plus 1 by R into dou by dou phi into J phi plus 1 dou by dou Z into JZ. What is JR? Here if you see this equation, what is JR? JR is 10R square Z and J phi is 4R cos square phi. But JZ component is 0. So if you substitute this in this equation, you will get 1 by R into dou by dou R 10R cube Z, 10R cube Z plus 1 by R into dou by dou phi into minus 4R cos square phi. So after differentiating this with respect to R and phi, you will get 30RZ plus 8 psi phi cos phi. Now using this equation, I is equal to volume integral of del dot J into dV. So here in cylindrical coordinate system, dV can be written as R into dr d phi dz. So dV is equal to R into dr d phi dz. So we can write I is equal to volume integral of what is del dot J, 30RZ plus 8 sin phi cos phi into dV is R dr d phi dz. So if you integrate with respect to Z, phi and R, so you will get the limits for Z is from 2 to 2.8, for phi is from 0 to 2 pi and R is from 0 to 3. So according to this equation, they given just R is equal to 3, but we will consider it is originating at 0 and ending at 3. So we will consider R is varying from 0 to 3. So that's why limit is considered from 0 to 3. And if you integrate with respect to R, you will get 30R cube Z by 3 plus 4R square sine 2 phi by 2 and apply the limit, then again integrate with respect to phi and apply the limit from 0 to 2 pi. You will get this and again integrate with respect to Z. You will get 540 pi into Z square by Z. Z is equal to 2 to 2.8. So after substituting that, you will get the 3.257 amps is the outward flow of current from the cylindrical surface for a current density is equal to J is equal to 10 R square Z AR cap minus 4R cos square phi into A phi. So next problem we will see the one more problem on current density and current, the relation between current density and current, that is a current density J is equal to 100 divided by R square plus cos theta AR cap ampere per meter square in the spherical coordinate system. The given J is in spherical coordinate system. How much current flows through the spherical cap when R is equal to 3 and theta is varying from 0 to pi by 6 and phi is varying from 0 to 2 pi. That is first case. What is the current flowing out from the spherical surface? And second case, the same total current as found in A. So if the current is A, same the current what is we obtained in case A flows through the spherical cap when R is equal to 10 meter, theta is varying from 0 to alpha and phi is varying from 0 to 2 pi. What should be the value of alpha so that when these are the coordinates, what should be the value of alpha to obtain the same value of the current which is obtained in the case A? So we have to find what is the value of alpha in case B. So if first we will take case A. So we know in the question they give us what is current density. If you observe the equation for current density, 10 cos theta R square plus 1 into AR cap. Here, if you observe this equation, it is depends on only one component, vector component, that is AR cap. So we can say this current density is normal to the surface area with respect to theta and phi. So surface area with respect to theta and phi. So AR cap is normal to theta and phi. So we can write the surface area which is normal to AR cap is d theta, the surface area with respect to d theta and d phi. So I can write now I is equal to surface integral of J dot ds. So if you use same technique, we can write volume integral of del dot J into dv. But here no need to use volume integral equation. We can directly substitute the surface integral equation because we know that this equation only depends on AR cap. So surface area, there is a surface area perpendicular to this is with respect to d theta and d phi. So I can write the surface area which is perpendicular to AR cap is R square sin theta d theta d phi into AR cap. So J dot ds can be obtained by taking dot product. So and I is obtained by taking the surface integral with respect to theta and phi. Phi is varying from 0 to 2 pi and theta is varying from pi by 0 to pi by 6. And the R value is we will substitute as 3. So we will get the current as 70.6858 amps. Now in second case we have to find alpha so that the value of the current remains as 70.6858 amps only. So same equation I will use, but the limit for phi will change from 0 to alpha. The limit for previously it was from 0 to pi by 6. Now theta limit is from 0 to alpha. So we have to find what is alpha to maintain current 70.6858 when R is equal to 10 meter. So we know the value of the current, it is same as 70.6858. So if you integrate this one with respect to theta and phi, you will get this one. Then so apply the limit and you will get the equation as 0.424525 minus cos 2 alpha plus 1. So after simplifying this, you will guess 2 alpha is equal to 56.9411 degree. 2 alpha is equal to 56.9411 degree. So you will get alpha is equal to 28.47 degree, so, or 0.4969 in radian. So this is the value of alpha required to maintain the same value of the current when R is equal to 10 meter. So in this calculation here, whenever I substitute theta is equal to pi by 6 or 2 pi, I have to keep my calculator in radian mode. Then you will get the correct answer. If you keep in calculator in this calculation, if you keep calculator in degree mode, you will get answer wrong. So keep the calculator in degree mode and calculate the answer. Here what we did is, because this I is equal, we use directly this equation because we know that the J is depends on only AR cap. So there is a surface which is perpendicular to that R is with respect to d theta and d phi. So which is ds is given by r square sine theta d theta d phi, and the normal vector is AR cap. So if you don't know which is the surface perpendicular to that, then you have to use this equation. So next we will see the properties of conductors and dielectrics in next videos. Thank you.